Welcome to This Explainer. Today, we are taking a totally fascinating journey that connects the everyday practical use of artificial intelligence with the absolutely mind-bending mathematics that actually powers it. We're going to start with a highly practical 4-week roadmap to mastering AI tools for your daily life. But we aren't stopping there. Once we've got a solid grip on the surface, we're going to treat this whole thing like an iceberg and take a really deep dive into the hidden, high-dimensional geometry that makes these language models actually work. Seriously, it's going to completely change how you view the tools you use every single day.
Okay, let's dive into this agenda. We'll kick things off with our 4-week timeline to master AI, the AI prompting framework, and choosing your specific path. Then, we take the plunge into the math with the geometry of language models, the Knight's move, and finally, the high-dimensional volume paradox.
All right, Section 1, 4 weeks to master AI and the K-shaped economy.
So you might be wondering about the big picture here. We are currently entering what's known as a K-shaped economy. Basically, those who adopt AI shoot upward, while those who ignore it are kind of just left behind. This whole revolution really kicked off back in November 2022 with the public launch of ChatGPT. Now, if you master AI right now, you are sitting in this massive 5-year advantage window before forced global mass adoption hits around 2030. Taking action right now ensures you are on the upward trajectory of this massive economic shift. Here is your highly practical 4-week roadmap. The biggest mistake beginners make is getting immediately overwhelmed by hundreds of different tools on day one. Please, don't do that. In week 1, I want you to stick to just one foundational tool, like ChatGPT, and use it for simple daily tasks. Then in week 2, you carefully expand to maybe 2 or 3 tools specific to your daily workflow, like something for research or building presentations. In week 3, you'll choose a specialized AI path. And finally, week 4 is all about forcing yourself to produce a real-world output, something you can actually publish or use in your business today.
Moving on to Section 2, the AIM Prompt Framework, Learning to Talk to the Machine.
Let's rewind to week 1 for a second, because your success really rests on prompt engineering. Now, what's really interesting about this slide is how the AIM framework takes a totally vague query and turns it into a high-powered command. First up is the actor. You tell the AI exactly who it is acting as, like a veteran technical recruiter. Then, the input. You give it all your context, like your current job, your years of experience, all that good stuff. Finally, the mission. You state exactly what you want it to do, like conduct a mock interview and give you harsh feedback. Transforming your prompts this way will drastically improve the output you get from literally any tool. Next up, Section 3. Choose your AI path, going from Explorer to Pro.
Right around week 3, you're going to transition from just an explorer to a specialist by choosing one of these 3 core paths. The creator path is fantastic for those in marketing or design focusing on generating high-quality content, images, and videos. Then there's the builder path, which is for folks who want to automate workflows or build software using AI coding agents. But the third path, the engineer path, well, this one is entirely different. This is for those who want to understand neural networks, deep learning, and the actual core of machine learning. While creators and builders are comfortably riding on the surface of the AI iceberg, engineers have to look under the hood. And you guessed it, that is exactly where we're going next.
Section 4. The geometry of LLMs. Let's look under the hood.
Using that engineer path as our anchor, it's time to plunge below the surface. So what actually happens inside the machine when you hit submit on that carefully crafted prompt? Well, this quote sums it up absolutely perfectly. Machine learning is awash in high-dimensional geometry. Essentially, anytime you're representing something with a long list of numbers, you can interpret that as a point in a high-dimensional space. Beneath your simple text prompt lies an invisible, incredibly vast geometric universe. It's not just lines of code, it's quite literally geometry. To break that down a bit more, here's what's actually happening. When you interact with a large language model, it takes your text, breaks it into little chunks, and turns every single chunk into a really long list of numbers. To truly understand how these models process language, mathematicians don't just see boring lists of numbers. They view them as precise coordinate points in a geometric space. But because these lists are hundreds or even thousands of numbers long, this space has hundreds or thousands of dimensions. And as you'll see, higher dimensional geometry introduces some deeply, deeply bizarre mathematical realities.
Which brings us to Section 5, the Knight's move, and calculating volumes.
So, the crucial point is, how do we even begin to measure shapes in spaces we literally cannot visualize? Well, mathematicians use something affectionately called the dimensional Knight's move. It's this really elegant, recursive, hopscotching formula that actually derives from the ancient Greek mathematician Archimedes. To find the volume of a sphere in a higher dimension, you don't start from scratch. You take the volume from 2 dimensions lower, multiply it by 2 pi, which essentially projects the boundary outward, and then you integrate that boundary to find the solid interior volume. Now, in calculus, integration introduces a division factor, so you divide by the number of dimensions, or n. Multiply by 2 pi, divide by n. This repeating step lets mathematicians walk safely from a simple 2D circle all the way up to an n-dimensional hypersphere.
But here is where it gets wild. Even with solid math, our human intuition gets completely shattered here. Let's compare our comfortable 3D logic with mathematical reality. In 3D, if you put a sphere inside a cube, it fits perfectly and snugly inside its bounding box, right? But in high dimensions, cubes become profoundly spiky. The corners of a high-dimensional cube are just incredibly far away from the center compared to the flat edges. Because of this, if you pack spheres into the corners of a 10-dimensional cube, and then try to inflate one single sphere in the center to touch them all, that inner sphere grows so massive it literally bursts right outside the bounding box of the cube itself. No way, right? It's mind-blowing.
Finally, Section 6, the high-dimensional volume paradox.
And this brilliantly illustrates the ultimate paradox. What happens to the actual physical volume as these dimensions scale toward infinity? Check out the peak on the 5-dimension bar here. As you go from 1 to 3 dimensions, the volume of a unit sphere gets bigger. It continues to grow until exactly 5 dimensions, where it peaks at a volume of about 5.26. But then, something crazy happens. At 6 dimensions, it starts shrinking. By 10 dimensions, it's already smaller than a 2D circle. And by the time you get to 100 dimensions, which, by the way, is still incredibly small for an AI model, the volume rapidly collapses toward absolute zero.
To put that into perspective, the exact volume of a 100-dimensional sphere is 2.37 times 10 to the negative 40th power. It is infinitesimally small. It's essentially nothing. Why does this happen? Well, remember that Knight's move we talked about? Every time you step up in dimensions, you integrate, which means you divide by the number of dimensions, n. As n gets into the hundreds and thousands, that denominator becomes a massive factorial that completely crushes the 2 pi numerator. The volume practically ceases to exist. There's one last high-dimensional quirk we need to touch on. Where does that tiny sliver of remaining volume actually sit? Well, in 10,000 dimensions, if you were to shrink a sphere by just 1 single percent, its volume effectively vanishes entirely. That means 99.999% of the geometric mass sits right on the razor-thin outer boundary. The deep interior is effectively completely empty. For AI researchers, this is a massive realization. When you're dealing with high-dimensional data, virtually every single data point is sitting right on the absolute edge of the space.
So, we've gone all the way from writing a basic text prompt to visualizing the vanishing geometry of a 10,000-dimensional sphere. The everyday tools we're using are built atop realities that completely defy human intuition. The only question left for you is this. Will you stay comfortably on the surface, or are you ready to master the dimensions beneath? Your 4-week clock starts right now. Get out there and start exploring.